Hi people, so we live and I'm here with some students from Campion College in Jamaica. Um, so they will be determining the topics that we do. Um, and the first thing they said was section D was the monster. Section D is electricity and magnetism. So what we'll do is we'll do this from a past paper perspective. Let's go jump into a past paper on that. The worst case scenario is that you get it for question 1. So you know the exam is like 6 questions. Question 1 will be the question with the graphs and everything. So if it comes in that question, they'll probably bring V equal IR or something like that. What? Yeah, save that to the end. So, but you all know what V equal IR is, right?
Yes.
What does the V stand for? And the I? What is the unit of I? Right, and the R? Right. So there's a bunch of small formulas in electricity. There's this V equal IR, then there's another one like P is equal to, give me P. P is equal to what in electricity? I squared R, but we usually in CXC we get this one IV. And then you have Q is equal to IT. What else? E. E is equal to QB. IVT, very good. So E is also equal to VIT. So I just kind of have it like EVIT. So these are some of the small formulas that show up in electricity. There's a few other formulas that can show up in this. There are the formulas with resistance, like in parallel, and resistance in series for total resistance. You all know that those?
Yes.
So resistance in series would be like what? Resistance in series, formula for resistance in series.
Resistance in series?
Yeah.
Resistance?
Resistance in series. I don't know your names. Resistance in series.
R1 plus R2? R1 plus R2?
Yes, that's right. So like RT would be R1 plus RT. Then looking good, eh? R1 plus RT. And for resistance in parallel.
1 over R. 1 over R.
And this is equal to what?
Total resistance?
No, 1 over RT. It's important to remember it like this. Now, this is the way I learn it. Some teachers will show you like the breakdown in this, like they'll find the LCM. So this will be R1, R2. R1 goes into this R2 times, R2 goes into this R1 times. So end up with a sum over product, but that's 1 over RT. And then they flip it around. So you get RT is equal to R1, R2 over R1 plus R2. But I don't really use this that much. So
We only use that if it's 2 resistors.
you only use that if it's 2. So that's why I just kind of like, meh. I don't even bother to learn this. I just learn these 2. So this one and this one. There are other formulas that can show up in electricity for transformers. What's the formulas for like transformers?
For what?
Transformers.
Any
Right. So what is that called? Well, we normally the turns ratio. So yeah, sometimes we use common and P over NS. So which one is direct? Which one lines up with the P and the S, the V or the I?
Which one lines with the S? The I, no. The I is the only one that's
Yeah, the I flips. So the V lines up. So it's VP over VS. And this will be IP over IS. So this is the turns. And what's the formula from here that normally accompanies the turns ratio formulas, all these formulas? Yeah, power. So in a lot of these types of questions, you'll see power pop up. P is equal to IV will pop up here. So yeah. All right, so these are your formulas that you can see. Let's just pull out a random question. I'm looking at the Cohen Springer website to pull out random questions here. Let's see. All right, so if they ask you to differentiate between AC and DC for 2 marks, what would you say? So what is in direction? How would you write it?
Sorry, I think you wrote the current one wrong for the transformer.
Really? Oh, thanks. So I wrote this wrong. Anybody on YouTube tell me? Yeah, so this is gonna be IS. I'll correct that. IS over IP, right? So the current flips, right? Differentiate between alternating current and direct current. Alternating current changes direction and magnitude periodically, whereas direct current flows in one direction only and is usually constant. But the usually constant part you don't need to put in. And the thing that changes direction is the current or the voltage, right? So that's your definition there. And if they ask, sometime recently they asked you to draw the electrical symbol for a transformer. Can you draw that symbol for? There's a few that show up in electricity. There's all these symbols that show up in electricity. You have it down? So let's go look at it because that's a free one math. Let me see if I could bring it up somewhere. Where is my for a crash course? 1 second, I'll get it. Anybody know the symbol for transformer? Try it, let me see. Yeah, something like that. and the fuse, you know, the symbol for fuse. And variable resistor, those are the top three, I think. Yes, two symbols of variable resistor. Right. So chances are one of those will come. And the symbol for alternating current supply, AC supply. All right. So I'm trying to find my document with the whole list. All right. Didn't sound in too bad. What about logic gates? You all know. So logic gates supposed to be one of the easiest parts. It's just like a little relaxation session in the exam. 1 second, YouTubers are just bringing up a symbols chart here. So all these symbols. So let me go through these symbols and tell you what popular. It's not that popular, but I mean they can bring it if they're feeling wild, CXC feeling real wild these days. Cells, battery cells, DC supply. They don't normally show DC supply, they say just use a cell. AC supply, switch. Like they wouldn't really show this, but this is to show that both of them connecting. The galvanometer is popular, but they normally bring it like this with the arrow. Semiconductor diode, extremely popular. This, I've never seen this. That's a rare Pokemon. This one, I see this all the time. Fuse, the fixed resistor, obviously, all the time. This is extremely common. I've never seen this as well. I've never seen that. The electric motor. But you should know it. It's on the syllabus, but I mean, I'm just saying it doesn't come. And then there's a next set of symbols here. This one, wires crossing over each other, not so much, just in circuit diagrams, you need to know about that. Never seen this really, This comes, no, yes, this comes, but normally it comes standing like this, the transformer. This came, right, last year, I think it came. This will come, this will come, this will come. These are popular. So logic gates. What do you know about logic gates, people?
And or not.
So you have to know all your symbols and how to populate the truth table, right? Or the trace table. So the symbol for and, wait, what's the first symbol? You should know the inverter, not, right? That looks like this. Then the symbol for and looks like this. Then your symbol for or looks like this. And then the no will do what? Right, so the no will just have a, so let's put this here. And the no will have like a dot in front of it. These have two inputs. And the NAND will have a dot in, like that circle in front of it, right? So everybody know about that, right? And then we know how to populate it. So like this is just an inverter. So like the in, the out, or let me just put A and I'll put B for out. So this is just 1, 0, 0, 1. But the others have two inputs, so A, B, and then the output, I'll call the output C in this case, right? So what I do is I'll always start off with 0 here, put another 0 there, put 1 there, put 1 there, and this one I'll put 0, 1, 0, 1. You all know about that? And then it doesn't matter. So like in the exam, it will come scrambled, but you should learn this order because it kind of helps to understand it. I'll bring up, let me just bring up my 12-hour stuff on this. Where is it? See if y'all can finish all these in the meanwhile. A, B, C, A. All they're laughing at is supposed to lock that down real fast. A, B, C. So this is a little bit of a 12-hour crash course that I did recently with some students in the student hub. So private student hub material you're going to see here. So yeah, we'll use those for our questions just now. So all of these are populated the same as 0, 0, 1, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 1, 0, 1. This is just to get all the different variations of this that could happen. But the output, so how you learn logic gates and have a lot of fun with it if you learn it this way is by the exceptions. So what is the exception for AND, for your AND gate? What does the AND gate do then?
It's only gonna be one in both.
Right, so that's what I learned. I just learned the French case. So it only gives 1 if both are 1, and then all the rest will be 0.
So the exception is about 1.
Well, the exception is about it changes. So which one? Like, what is the exception in the OR? What does the OR do? So this is the only exception here, the 0. So I learned that. Nice. Yeah. So this will only give me 0 if both are 0. So all the rest are 1s. And then that's all you really need to learn, because the NAND is the reverse of the AND. So the NAND works like this, 0, all these zeros will turn to 1. So you'll have, where's my research? So you'll have 1, 1, 1, 0. So it flips this. It's just like a NOT gate in front of the AND or behind the AND. And this one will turn to, this will turn to 1, and then we get 0, 0, 0. So everybody have fully clear on that, right? Yeah. Makes perfect sense. All right, so let me see where this went. So in the crash course, we talked about half-wave rectification before we went into this. That's where the syllabus is. The NOT gate, the AND gate, the OR gate, the NOR gate, and then questions. So what they want us to do in this question is like populate the table. And this is how it will come in CXC. Now notice I have a different technique. Most likely they will write the numbers for you. But if they don't, I have a different way to do it for like if there's 3. So I showed you what to do if there's two inputs. So like if there's two inputs, A, B, and you're trying to find the output C, you would do 0, 0, 1, 1, 0, 1, 0, 1. That will give us the three types, right? But if there are three inputs and you have to put it in for yourself, A, B, C, and let's say the output is D, what I will do is put 0, 0, 0, 0, 1, 1, 1, 1, then 0, 0, 1, 1, 0, 0, 1, 1, then 0, 1, 0, 1, 0, 1, 0, 1. Are you find the pattern there? And this will give you all the different possibilities. So this is like if you have the input, right? So, and then you can figure out the output based on whatever. So let me go through this. Now, the reason why I said the best way to do logic gates is to learn the fringe is because watch how this will work out, right? Input, I need to reload this. What page is on here? Page 164. Dun, 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 dun. So, yeah, there we go. So this is the NOT gate. The NOT gate is special because it only has one input. So for A, we already have, so what does it do? What does the NOT gate do? Everything will flip. So I could go to D and everything I'm seeing on A, flip it. That's the fringe, right? So you just flip everything. So D is the inversion of this. So 1, 1, 1, 1, 0, 0, 0, 0. Making sense? And then for E, where's the inputs for E? So you have to go find the inputs now. Where's the inputs for E? D, we can see that, right? The D and the B, right? So the D and the B. Now, what type of gate is this? NAND. And what does the NAND gate do? It flips the AND gate. And then what does the AND gate do? What's the exception? Of both are ones, right? So 0, 0, 0. Well, we could. So I have it in my mind, but I'm just doing it the long way so that everybody can see what's going on, right? So this would be 0, 0, 1, 1, 0, 1, 0, 1. So this is your AND gate, but the NAND gate, now you know that this should flip. So you would do for the output 1, 1, 1, 0. So what's the fringe you're seeing here? What's the exception with the NAND gate? They both have to be 1 and we're going to get a 0. So that's all you have to do now in the table. Just go and look for any where you see D and B are both 1s. So where you see D and B are both 1s here, and that means that have to be a 0. Both 1s here, that has to be a 0 anymore? Nope. So then all the rest are going to be, instead of having to go through everything and waste your time, right? So it's just, this is cake and ice cream. That's it right there. So this is E, this is C. What type of gate is this? OR gate. And what does the OR gate do? What's the exception?
When they're both 0.
When they're both 0, you get a 0. Every other thing will give you a 1. So let's go and see when E and C are both 0 to put a 0. E and C. When E and C are both 0 here, right? So I'll put a 0 there. That's it. That's the only time I'm seeing it. So then all the rest will have to be E and C. Just want to make sure. Yeah, all the rest will have to be 1s. And at the end of that, and let's give you real marks for this. Yes, marks. Well, physics, they love to give you marks for everything in physics. And then they discuss the impacts of that. That's what's next in the syllabus. So let's just... Electronic and technological advances in society. You're going that. You just make it happen, right? Okay, so let's go back to the questions. Complete the statement below. Transformers work on the principle of mutual. Transformers work on the principle of mutual what?
Induction?
Yes. Mutual electromagnetic induction. That's now I'm about stuff. So So transformers work on the principle of mutual electromagnetic induction. So a question that they like to follow up with that is basically asking you why you can't have a DC transformer and you need the directional. So transformers only work in AC. Only possible in AC supply. Yeah. And no longer I teach students in a class like this. It's been online so long. So it's very strange for somebody to ask me to go and use the bathroom. Just go. State two advantage. Here's another question that comes a lot. What are the advantages of using AC instead of DC in transmitting electricity? AC versus DC in transmitting transmitting electricity. Why do we use AC?
Switch the direction of the current.
Spell electricity, right? So why do you use AC over DC? Why AC is the boss when it comes to like transmitting electricity over long distances? Right, you'll get zero if you put more versatile. Let me see if YouTube has the answer. To lower it and change direction, more efficient. So this is one, you know a lot of these questions in CX, you can wing it and say more efficient. Nah, you can't say more efficient in this. And Samantha from YouTube, you supposed to know that, right? But she's to lower it kind of has the idea. Remember, I told you all transformers only work with AC. So we could actually change the voltage. So stepping up and stepping down. Yeah. And DC, when we transfer in AC, we could use high voltage. This is the main reason actually. We could use high voltage, low current. And the losses happen when you have high current. Are they locked in? So the losses happen when you have high current. So by having high voltage, low current, you have low losses. Energy losses here. Energy loss. Why I can't write energy, boy? Energy losses. And then, so that's one. And the other reason is you can step up and step down. So typically, power stations will produce high voltages. We don't want those high voltages coming into our house. So AC can step up and step down the voltage. So it became apparent very quickly that AC is the best when it comes to transmitting. So AC, you can use high voltage, low current. So this is low energy losses in transmission. All right. Next question was. All right. So
step up, step down part is about like protection.
This.
Transmit high voltage energy to certain places.
Right. So you don't want high voltages coming. You don't want the same voltage from the power station coming through here because you're dead. So you want low voltages in like your household use. Yeah, so the next question is about maths. So, this unit physics, you will have to memorize a bunch of things and then do some maths. So this is the maths here. Read that question, see if you all can get on top of that. So the thing with electricity, you're always, once it's like one of these types of questions, you're always going to be doing one of the formulas that we mapped out before, either the transformers or the P equal IV. So what we're going to pull out here. Firstly, you need to know the types of transformers. So just a quick, because I'm a little confused now. You know what to do? You know what to do? You know what to do?
Is it not just the formula?
Yeah. So a mobile phone charger contains a step-down transformer. So these things that we charge our phones with are like mini transformers, eh? So, which converts the Tyrell noise outside here, but are they making me miss a party to come and teach physics here, right? Which converts the input of 220 volts to a working output. So it's stepping down. So a step down transformer, if you have to draw it, the number of turns on this side, sometimes you draw this kind of thing on it, right? So the number of turns on this side will be more than the number of turns on that side, right? And remember the relationship we have, Vp over Vs is equal to Np over Ns. So what I want to know is converts that's just the same. If the output current, so we know what do we know? We know Vp is 220. We know working output voltage Vs is 5, which means you could find the turns ratio. You could find the ratio. And the output, so that is Is. Everybody understand that? Is 120 milliamps. Should note that this is milliamps. And then we need the input current. So that's 3 marks. We need to find Ip. What's the relationship between V and P with this? Samantha, have it there on YouTube.
Vp over Vs equal Is over Vp.
Right, because it's flipped with voltage and current. Well done. What's your name?
Akira.
Akira? Is it Akira?
Yes.
All right, okay. So Vp over Vs is equal to Is over Ip. That's what you said, right, Akira? So what we're trying to find Is. So what I would do is just substitute it one time and bring it across. But if you want, you could bring this across one time, like have Vp over Vs is equal to Ip is equal to Is. Or you could have just substituted everything here one time. 220 over 5 must be equal to 120 over Ip. Sorry, we didn't want this. I made a mistake. So this wouldn't even work. We didn't want Is. I thought we wanted Is. We wanted Ip. So yeah, everybody know how to work out this from here, right? So if I had to work this out from here, I would probably write Ip is equal to 120 over 220 multiplied by 5. And what the answer is going to be? Yes, I am in Jamaica right now. Terra, whatever your name is. Cross multiply thing. I'll give me some answers there. $2.73. And then what do you write here? Milliamps. So you have to watch the units, right? Yeah, physics will guaranteed take away a mark from you if you do that. So then the next part was to determine the power supplied by the secondary turns. So they said milliamps, so we kept it in milliamps. So determine the power. So every time you have something to do in transformers, what's the next formula that you're looking out for? Power. P equal IV. And since they said the power in the secondary, we're going to use Is and Vs, right? And we just found Is to be 2.73, and I'll put times 10 to the negative 3. Why did I do that?
Wait, didn't you just find IP?
Oh, shucks, I found. Oh, my bad. Very smart. Akira, you got yourself 120 times 10 to the negative 3, and then we multiply by Vs, which was 5. And then how much we get in there? Nah, 0. What? 0.01. Nah, I didn't get that. 5 12s are 60. So it's supposed 0.6. So 0.6. I expecting that 60. So 0.6 watts. Can't go wrong. And then the next part of this question is, so what could follow up a transformer question if it comes in the exam? After you do this turns ratio stuff, some one of this VP, VS, NP, NS, over the reversal. What's the last part that could come in this question? Anybody knows? So the last thing that could come in a transformer question. Efficiency. So they can bring efficiency. So something about efficiency usually follows up a or sometimes they start off with efficiency and you need to work it out. Everything using a percentage. So the question was, if there's a 10% loss of power, what is the actual power? Well, that's 3 marks. That's two free marks. So what would you do for this? Just work out 10% less of that, right? Yeah, so, and the answer is going to be power. Why did I put V? Is power working out? Why not scribbling out? Actual power is going to be, you all understand why I write 0.9 times 0.60? So this is like 9. So I just take out the 10% out of the 100 one time, so you get 0.9. So this is like 90 over 100. And you get 0.54. What's cooking?
Wait, what's the 0.9?
90%.
So this is 90 over 100. Yeah. All right. What topic you all want now? More electricity? What part of electricity you all want to talk about?
Yes.
Oh, this. Okay. Well, with Fleming's, it's good to have like a mind map with what's happening. So let me talk about how I would mind map this, right? So which one you think comes first in like your learning, the left or the right? And on the left say left, these on the right say right. Where's the left? So the left hand and then the right hand. So like in my mind, I would learn like the left hand first and the right hand after. And so this is Fleming's. And what is, both of the hands use the same 3 fingers and both of the 3 fingers mean the same thing, right? So we could learn what the fingers mean. What would the thumb mean? Force or force, or some books will have motion. Trust, yeah. So the thumb is like the force, the motion, trust. Then the index finger would be what? The feel, yeah. And this is the magnetic field. And it points from what to what? Yeah, so this points from north to south. And the last finger in the middle would be current. And this points from what? This is conventional current. Right. So the direction. Right? Yeah, so the direction a positive charge will want to go. Okay, great. So Fleming's left hand, you use your left hand like this. By the way, you don't need, they probably shouldn't have teach us this. They should have probably teach us the palm version and the current is coming out of your palm. This one easier to see. But since everybody uses left hand and right hand, we'll work with that, right? So the next thing in your mind map of Fleming's left hand rule is like, what is the use case for? So one comes first, the left hand, and what part of the syllabus that show up in first? Fleming's left hand is solving for, no, not generators, motors. And this one, Fleming's right hand is solving for generators. So this one is motors. So this one deals with motors, this one deals with generators. All right, so that really helps in the understanding. Now motors, so in both cases, you would know 2 of the fingers and you're trying to find out 1 of the finger. So in Fleming's left hand, which finger it is you're typically trying to find out? The thumb, the thumb, the index, or the middle? Which one are you trying to find out? So it helps to think in a motor. What does a motor do? What is the result of a motor? Movement. What do you put in? You put in the current. So you're trying to figure out the force. So this one is always about figuring out the force. So Fleming's left hand solves for the thumb, the force. Yeah, make perfect sense. So this one is the current, which we know. The current which we know, and this is the field. This is the field. Yeah, that's correct, ready? And this one is the current. This one is the current. So we have the force, the field, the current. So we know this, and we're trying to figure out the force. So we actually use Fleming's left hand in another situation. Like if you have a charge carrying conductor in, there's a few cases where this will use as well. So take note of this. So like if you have the wire in a field, a wire in a magnetic field, that question could come. How the wire would move, which direction? So wire in a field. And there's one other case where you'll have to whip out your Fleming's left hand rule. What other case is that? What other case do you remember of something being in a field? This is radioactivity. Radioactivity is a lot of fun too. Radioactivity is 3 marks. Radioactivity, when you have to determine how the alpha, beta, and gamma particles will move in an electric field. So we'll talk about that right after, right? So we'll talk about this right after. So these are 2 fringe cases of using Fleming's left hand. Okay, and then Fleming's right hand will be the mirror of this. And what you're trying to solve for in Fleming's right hand? The current, because a generator generates electricity. So you're trying to find the current. So this one, Fleming's right hand, you're trying to find how the current will flow. So you have the movement or the force, you'll see, right? So we work with force. We have the force. We have the field. So you always have the magnetic field. You're trying to find the current. Right, Akira? So you're trying to find the current. So good. All right. So that's the mind map of Fleming's left hand there. Fleming's left and right. Now we need to know how to get it done. So let's do some examples. Oh, before you do Fleming's left hand and Fleming's right hand, there's like a baby version to this called, let's see, like to show how the circular movement of the field will be the right hand grip, right? So you point your thumb along here, and if you grip that with your right hand, you will see that your fingers curl this way. So that means it will be going in this scenario. That's it, provided the current was going up. Provided that the current was going up the wire, which is, by the way, like if this is positive and this is negative, that's that. Everybody understand the right hand grip? Any questions on the right hand grip there? We good? So that's called the right hand grip. So that could come as well. The right hand grip is used in scenarios like this. There's one other place you could use the right hand grip. Where's that? That might show up.
Is it a solenoid?
Yeah, the solenoid or the coil. The thing, by. So this, like if you need, so this question is particularly notorious for students just doing really badly in this question. So the right hand grip, and determining like who is north and who is south, or which direction a galvanometer will deflect in that. So we could come back to that one too if you only want. But right, so let's continue with the left hand and the right hand. Motors, generators, left hand, right hand. Let's see if we can get a question on that. So the question on with Fleming's left hand rule, like the big questions are usually juicier. They come for like 7 marks. And it's like you have to describe the whole principle of how a motor or generator would work. You all can do that?
No.
Let's go. So the first one we'll deal with is motor. Who is Fleming's what? Fleming's left hand, yes. So let's set up a magnet like this. This is how it's usually shown in CXC. You'll have like your north here, your south here. Then you'll describe your coil. You'll have your coil. Ah, that's very important. So I'm glad that you're talking about that.
Split ring commutator.
Yes.
Yes.
So, okay, hold up. So they're talking about the YouTube, they're talking about and motors and generators, the little thingy at the end. So in motors, it's called a commutator, but there's something that I say before. There's a commutator, and then there's a word for the ones in generator. So in motors, what is the word? Let me hear.
Split.
The motors is a split ring commutator, and in generators, it's a slip ring. You just need to say slip ring. Slip ring. So generators be slipping, motors be splitting. Right. So remember that. So yeah. So we're gonna put the split ring commutator here. And attached to the split ring commutator is what? Carbon brushes. There's no cheating, right? Carbon brushes. And that will go to your whatever your battery or whatever you run in the motor on, right? So we have that so far. So these are your carbon brushes, which are like spring loaded onto this. Meaning that you have a spring pushing it onto the commutator. Yeah, not too hard, just so that it stays in contact, except where it reaches this 180-degree mark, it will break contact. And that's a whole part of your definition there, right? Actually, let me just find it here on the I need to be paying me for this music and thing again in the background here. Campion, I need to come up with the money. All right, so this is action of a DC motor. So this is the exact drawing I draw. Just my drawing was looking better. So it's the appearance of hanging up on there. So we have the north, we have the south. Now they could switch it up on you, and they could put north here and south here. That's where Fleming's left hand rule come into play. So you will have to use Fleming's left hand rule to figure out what direction this will go. So like they could draw this to you and ask you to describe this, boom, 7 max. Can you do it? So it's important when you're doing it to put A, B, C, D here. That will make it much easier for you like to label the sides when you're describing it. So what's happening? What is the thing that you're trying to figure out with this? What is the product of the left hand, Fleming's left hand rule? The force. So therefore, this is what you're trying to figure out, what direction this thing will turn. So that's the result, because you actually putting in the current and you already have the field, current field. So let's look at AB here, using the left hand. Now, those who watching on YouTube will see that I have my right hand up, but they could testify as my left hand up, right? But it flips. So you'll use your left hand and you will line it up there, and I want you all to tell me what direction AB is going to move. Go ahead. Have fun. Tell me when you come up with the answer. You say what? You said down. That side saying down. Down. Let's show body down. Yeah, it's going down. So, right. So you're gonna take your middle and point that in the direction. You see the red arrows going here, and then the field north to south. So then you'll end up pointing down one time as a point like that, right? So this is going to end up going down. Now, what I was saying earlier, it kind of gets easier. You don't need to do all these kind of gang symbols if you just do it this way. So let the current come out of your palm. So let your palm point out to the current, and your thumb will immediately tell you the answer. So the current is coming out of your palm. So remember,
here, it'll be going 8 towards
because remember your current is the middle, but you might as well just make that your palm and let that go down.
So if it was this way, it's
Now use the Fleming's left hand rule again to find what direction DC will go.
So this is if it will go to this way, then it will be going 8.
Oh, the arrow is going that way. Oh.
So it has to go out. And then it's
What's your name?
Hannah.
Hannah, right? Hannah. So this yeah. So you'll use this finger for the north to south. This it's coming out of. I'm doing DC now. So DC, the current is coming this way, and then you'll see the motion here must be going up. It's going from C to D. Because remember it goes in a circle right around. So can you see now that it's like a couple of forces? One is moving down, one is moving up. So that's going to cause this to spin which direction?
Oh, I guess it's
Anti-clockwise. So this is the money in the CXC. This is where your marks reside in. This is the house. This is the home of your marks here. So let me see how you put this in if they bring this whole thing for you, right? So when the switch is closed, the current flows through the carbon brushes and the commutator into the coil. Keep in mind, this is the split ring commutator. So the motors, you want to make sure you have the word split and commutator in it. Split commutator, split ring commutator, and generators is slip ring. It's just one whole circle, right? So there's a split in this. Somebody late to the party here, boy. Okay. So the current is flowing from A to B and C to D using Fleming's left hand rule. A downward force is exerted on AB while an upward force is exerted on DC. You all see all of that already, right? This is just how to put it in words to get the marks. And then this is called a couple of forces. It will create a torque or momentum and cause it to spin in an anti-clockwise direction. Another important mark collected here, you have to say the direction that it's going to spin, whether it's clockwise or anti-clockwise. And eventually, this is the next set of marks here. You need to kind of explain the working of the split ring commutator. So usually, if they bring this, you're bound to get something with the split ring commutator, have to. So you need to be able to put this in words, what's going to happen here. This definition that I have here needs a little tweaking. Eventually, at a certain point, the split ring commutator loses connection with carbon brushes at 90 degrees. However, momentum, this is a nice way to do it. The momentum will cause the coil to continue spinning until it comes into contact with the circuit again. Now, the whole idea here is that if you didn't have that setup, this will keep spinning and the coils will wrap up itself. And in fact, that wouldn't even happen when it reached halfway, because the current in CD is moving this direction. If this goes over here and keeps that current moving that direction, guess what? It will want to push it back up. So it wouldn't get that downward, upward turn around like this. So what happens is that the coil will keep bouncing backward and forward like this. So that's why we have this split ring commutator.
Wait, say that part again.
So imagine if CD, right, came all over to AB's position, right? So we have CD here now. The current in CD is actually going this direction. This direction. So if you use Fleming's left hand, that would want to push the coil back up. Right? Right now, AB, the current is moving this direction, because the current is moving that direction is the only reason why it's pushing it down. So think about it. If we had this going up, 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 and then it wants to keep going up, 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 it will just keep bouncing backward and forward. Yeah. So what we do is have this split ring commutator, so it breaks contact. It breaks contact and doesn't stay connected to the negative side of the circuit. So DC, when it splits and come around here, will be connected to the positive side of the circuit. So current will start flowing the opposite direction in CD. So that means we'll get our continuous circular motion. That's the money part in the split ring commutator. That's the whole point. There's a really nice video on YouTube on that. You can look it up if you want to see it like in action. There are plenty of videos on YouTube on that.
So that the commutator changes what direction that the current's going to flow in each other.
And yeah, in CD and A. So that's the point. The split ring commutator changes you'll have to write that in the exam if it comes, most likely. The split ring commutator Come in. The split ring commutator changes the direction the current flows in, and you would label the part of the circuit in A, B, and DC, so that the axle could continue rotating in one continuous direction, anti-clockwise. All right, so that's your motors there, 7 marks. Let's talk about the generators. It should be here somewhere. This is your generator. Notice this one is just called a split ring, right? So this one doesn't break contact at all. What is the thing we're trying to solve in a generator? Firstly, we're using the right hand and we're trying to find the current, which means that the motion is provided. How is the motion provided, by the way? What provides the motion? What causes the thing to spin in a generator, in a power station? What's the magic words that they always making you say in physics? Starts with T. T-U-R-B. Turbines. So the turbines cause the spinning motion, and the movement of the turbines usually comes from steam. Yes, so you'll either have your burning your natural gas, your oil, even if you're doing a nuclear power station, the nuclear power station heats up steam, heats up water and creates steam. So the types of power plants, you got a roll? You're going? Oh, so the types of I see a standard now. The types of power plants that don't use steam will be like windmill and hydroelectric, where like dams and stuff, where they just have the water falling through, and that will turn the turbine. All right, so yeah, so the turbine's turning, and so we have the motion. So if this is turning, if they said that they will provide which direction it's turning for you. If it's turning, what the direction is? It's clockwise in this case. That means CD is going what? Up or down? Down. And at the same time, AB is going up. And so use Fleming right hand to tell me which direction the current will be produced here. Would the current come out of the paper or into the paper in this case? The answer now is what is coming out of your palm. It's going from where to where? C to D or D to just C? Where's it?
From C to D.
So yeah, point your thumb down and you point this from north to south and you see out of your palm, C to D. Yes, it's going from C to D. Or you could use it like this and you'll see that your middle finger is pointing this way, out of the paper. Everybody seeing it? You're feeling comfortable about it? You're holding up the wrong fingers. It's these two, right?
Because he said it's moving anti-clockwise direction, so CD is going down, that's of course.
Yeah, CD is going down. So point your thumb down.
This is going down.
This is going north to south. And you see, and that middle finger is pointing from C to D, right? Right. So that's why you can just do so. And what about check the AB side. A to B on the AB side, right? Which direction is the current going? On the next side, the current is flowing from A to B or B to A?
It's going from A to B.
It's going from A to B. So what will happen is just you'll end up pointing your thumb up this time and you'll see, not to south, so you'll see the current flowing this way, or like this way if you use this. Everybody catch that? Yeah. A to B. A to B, C to D. So it's going around in a circle like this. So that's the direction. So that's where the money is on this. So it's the same thing. The movement is provided by the turbines, well, it's in reverse kind of way. And it's clockwise movement, causing C to D to move down, A to B to move up. Using Fleming's right-hand rule, we can show that the induced EMF will be moving in the direction from C to D and from A to B. So current will be leaving from A, B, coming to C, going to D, and that's the direction of the produced EMF. This galvanometer, if they ask you, will turn in this direction to show that like
Which direction?
to the right. It's like current blowing it down as it's coming through there. If the current was flowing in next way, it will. Okay. So this is the direction of positive current flow, right? Conventional current.
Like, how does the galvanometer part, why is it going that way?
So like if current is flowing this way and a galvanometer was pointing straight, it will point like it's deflecting, being deflected by the current like this.
So it had a way the current's like.
Yeah, so cool. All right, any questions on that? So that's Fleming's left hand and right hand. I said I will go one time after into investigating. So there's like 3 types of radiation. What are the 3 types of radiation? Alpha, beta, and gamma. And there's a lot of little small things that they can ask you on that. Alpha is basically what type of particle? A helium nuclei. So they could either write alpha 2, 4, 2 plus, or they can just write helium 2, 4, 2 plus. Beta is basically what? Electron, like a fast moving electron. Gamma is energy. So it's on the electromagnetic spectrum. So EMR, electromagnetic radiation, right? So gamma is on the same spectrum with light, visible light, microwaves, radio waves, moves at the speed of light, but just very high frequency. So high frequency. So we can see that only this has a charge. Only the first 2 have charges. So only the first 2 would really be affected by a magnetic or electric field. Well, it depends on where the magnetic field is, and that's a trick question, I think, in the multiple choice. Gamma, not really affected by electric or magnetic fields, not affected actually. But that's not the only way that they differentiate the 3. There's like 3 ways. There's the cloud chamber. There's the what stops it. There's the electric field. There's the magnetic field. So all of these are ways that we can get to differentiate the 3. So if they bring it, some one of these must come. Cloud chamber, what it's stopped by, the electric field, magnetic field. Also useful would be like the type of equation for decay. So you don't know how to come up with the equation for the alpha decay and beta decay? Not yet. Equation for decay. The silence is telling. So let's go through them. Let's go through these 5 that we have so far. And radiation. Well, that's not all of radiation. There's more like the graphs where what will be on the graphs? What usually comes to the graphs? Half-life. Correct. Half-life, which is a lot of fun. Free max half-life. And if it comes in the question 1, most likely they'll bring that. And what else? With radiation, the question could go along a different path. It could go along a equal MC squared, where you'll have to find M, the change in M, which is called what? Change in, equal MC squared. That's Einstein stuff. C is what? C stands for the speed of light. M is the change in mass, aka the mass defect. So this is what you usually work out. They make you work out the mass defect. And how do you work out the change in mass? There's a formula. The change in mass is the mass of the products. No, the mass of the reactants minus the mass of the products. So that's why you work out, and then you plug it in. So radiation is a really small section. E is a really small part, but there's a lot of little tricks and things with that small part. All right, so let's do the cloud chamber first. So in a cloud chamber, what happens with alpha? straight streaks, right? So alpha, you're going to get these kind of straight thick lines like this. What happens with beta? Squiggly. Now, why is that happening? What is the cloud chamber? The cloud chamber is like, what is it like? A cloud of I can't remember what it was. Is it like steam or something like that? All right, whatever it is, and the alpha particle moves through it, and what we are seeing is the movement of the alpha particles through it. Who's calling me here? 876. That's Jamaica, right? Hello. Yes. So, 5 a.m. you wicked. So what does gamma do? So by the way, the cloud chamber is really like an ionization chamber, right? So it's like a test of ionization. Why you get these thick streaks is because it has high ionization power. So because remember it's 2 plus. So as it goes through the air, it ionizes the air, and we can see that streak, that thick streak coming there. Beta is a little more light, so it gets bullied by the air particles and will be spriting all over the place. The cloud is super saturated alcohol vapor. The ionized gas leaving behind trails of tiny liquid droplets, much like a jet leaves a contrail in the sky. Well done, Kirsten. Kirsten is one of my bright students from the student hub. So the gamma particles, they have no charge. So what do you expect to see in the cloud chamber? Right. So little wisp. So if it has no ionization power, why do we see these little wisps then? Why do we still see? Shouldn't we just see nothing? Something about electrons. Remember, it is. Hello. I think. Yeah, so the wisp is because there's high energy. So the energy actually tells the electrons, like let's say there's electrons in the outer shell. These electrons are always looking for excuse to bust out. So the energy will give them, the photon will give them enough energy to escape. So it's like, although it doesn't ionize anything directly, these wisps that we see are tiny electrons just running out. So that's that. So that's the cloud chamber. Cloud chamber is straightforward. What stops it? What stops alpha?
Paper.
So a sheet of paper. What stops beta? Aluminum foil. And what stops gamma?
Lead block.
So lead or meters of concrete. So some inches of lead or meters of concrete, right? Electric field. This is how I spell field, by. I didn't nobody can stop me here, by. Electric field. So the electric field now, and I usually say like field too, yeah? So electric field, electric field. Right, so how they show electric field is using dots like this or using X's. What does that mean? What does the dots or the X's mean? So X means going in, that means it's coming out. What I say all the time to my students to try to help memorize that is if you look at the back of an arrow, right, Hannah? If you look at the back of an arrow, and if this arrow was coming towards you here, what would you see? At the pointy part. So like if you're watching the arrow there, you would see a dot coming towards you. But if you're behind here, you would see I don't know why it's called that part of the arrow, these little feathers and things like that. You see the X. So this is going in, this is coming out. So this is where Fleming's left hand come back in. Fleming's left hand rule come back in again. So if I send along alpha down that field, what will happen? Yeah, but which way he's gonna bend now? So keep in mind, CXE have ways of changing this up, so you can't like just memorize it. Like you're gonna always bend down, because sometimes it might say coming out the paper or going in the paper. It depends. So if I send alpha along this, use your Fleming's left hand rule to determine which direction it will go. So this is electric field. Let me get a new page for this completely, right? So electric field, how they respond in an electric field. Let's do it again. So Kirsten online is saying it will go down. See if you all agree with her. Files you all agree with her because she's always get everything correct. So if I throw alpha down this line here, what will happen? So let's say the alpha is going this way. Which way will it curl? Up or down? So use Fleming's left hand. Which direction is the electricity going? Is it going this way or is it going this way? It's going the same direction as the alpha because alpha is positive, 2 plus, and conventional current flows in the direction of a positive charge. So boom, so you know which way to point this. And now which way the field is going? In or out the paper? Out. So which way will this turn, the red line? If you have the current going this way, field going up in the air, can you see the thumb is pointing towards your chest? You need to practice this because your fingers, they all need to be at 90 degrees to each other, right? Which one did I say? Did I say electric field? I should say magnetic field. Oh my gosh. Oh, my bad. That's my bad. That's why sis was right back watching. This is magnetic field. So yeah, this is magnetic field. My bad. So the magnetic field is going up. Yeah, bless her. So this is going up. The current is going this way. So can you see that this is pointing towards your chest? So therefore this one will curl how? Down. But watch the way it curls like this. So if I have beta now, beta is negative, which direction will this curl? Well, we could obviously guess that this one will curl this way. Now it's important to note that this curls faster than that because beta is lighter. Everybody locked in there?
Yes.
No? Confused?
Like I don't get this whole magnetic field going.
You understand what the dots mean?
No.
The dots mean the magnetic. Pretend like there's a north behind in the paper somewhere here. There's a north in the paper here, and out of the paper there's a south. So the magnetic field is coming up and out the paper. I still draw it at an angle, but it's coming out. So this is like the tip of an arrow coming out towards me, like if you're watching.
There's a chamber here, and then you're saying that there's a north here.
Yeah.
And then the south is on the other side.
Well, just the other way around though, because it goes from north to south. And this is coming out the paper.
Oh, so the north will be here,
Mhm.
and the south is here.
So like if the paper was drawn like this and I put the dots on the paper, and this is the flat piece of paper, flat plate, there's a north pole behind the paper and a south pole here. So what is happening is the field is going through the paper like this. So this is the field. And then what we had was the alpha particle coming along here, getting hit perpendicularly by the field. The reason that why it has to be like this is because if I had the alpha particle like this and I put the north and south here, nothing would happen. They must always be perpendicular for each other for movement. So that's a trick question in multiple choice. All right, so it's coming out the field, out the paper. So you'll understand like this is showing the magnetic lines coming out of the paper like that. That's why I point my finger up. It's coming out of the paper.
Oh, so. What are we using here? Or left hand or right hand?
Left hand, you want motion.
So it's here. Oh. Right.
And then
And then the current, this finger, is going this way.
The current is going.
The current is going the direction of the alpha. So watch which way your thumb is pointing.
Do they give you the direction of the alpha, or do you just have to know that?
What they do in these questions, the last question that came like this was, I think they just had either X's or that's, let's say they had an X. And they actually put they tell you to draw the direction alpha, beta, and gamma will go. Well, everybody can always get a mark with gamma because gamma not going to be bothered. But now you need to figure out which way the alpha and beta will go.
So this is going out the paper.
This one is going in the paper
In
now.
the paper.
So now you point your finger down.
Okay.
So like if you want to do alpha, let's say you wanted to do what will happen to alpha. Alpha, remember alpha will go in the direction. So you're down, then you put the current like this. Because the current is going that way. Up.
Going current.
Yeah, because what the current is going up.
So then what's this?
So then it's going to turn to this side as alpha. So the movement is going to happen like this.
No.
So
Okay.
where's the current going? Where's the amp? Wait. This is the field. This is the current, and we're trying to figure out the term. So we just need to point these in the right direction, and this will go the right way. So the magnetic field going down, and which way the current is going?
going this way.
Right. And
So
what?
then this is going that way.
Correct.
So different person.
Wait, so how do you know which way to bring it?
The X.
How do I know which way the?
Magnetic field.
The X represents like an arrow. So think of the X
Oh,
as
I
like
mean the other one.
the current, because the alpha particle, whatever way our alpha particle moves, is the movement of the current. Because alpha particles are what? Positive. So since they are positive and conventional current flows in the direction of a positive charge, once an alpha particle starts moving, it's moving in the direction of current. Beta is tricky because a beta particle, wherever it's going towards, current is actually flowing the opposite direction because it's negative. Do it again. What's your name? You are the person who messaged me. That's you? Oh, Ariane.
So this is going in the paper.
Right.
The current.
It's going the direction of this arrow here.
The gamma arrow.
It's going that way.
This way.
Yeah. Mm.
So then I know this.
Mhm.
Yeah. So it always goes in the direction of the gamma.
Yeah, this way.
Well, what's happening here?
This is going this way.
You could think of it like we started off here with nothing except a magnetic field, and then we came up with the three sources. We have them here, alpha, beta, and gamma, and we tell them go out and we can see what happens. So all of them shut out in this direction. Now we want to see if they will curl. We know that gamma will obviously not curl because it's not affected by a magnetic field because it has no charge. Alpha has a charge, positive. So because it's positive, movement of the alpha is up, so that means movement of the current is also up, because current follows a positive charge. So far, so good. So, what is Campion College? College with champions. Somebody say, I think he's helping out one of the poor schools down in Jamaica. I'll need to defend on yourself. Come on. Anyhow, so you point down and the current is going up like this. So you see the movement is going to go that direction. So this will turn like this. Now you have to put the turn slight with alpha. Once you figured out alpha, it means that you automatically figured out beta. Beta will go the next way, but make the turn sharp, and the turn actually turns till it goes backwards. In fact, if it stays in the field, it will turn into a circle and just keep going like this forever and ever. So why is this turning this way? You can use Fleming's left hand again. Now this one is tricky. Why is it turning in the next direction? Remember, we pointed the field down, and you might be thinking to point the current up again, but the current is not going up. Since this is negative in charge, it's going down. Whatever way a negative charge moves, a current is moving the opposite direction. So it's going down. Conventional current is down, so you'll end up pointing your thumb this way. So this will curl this way.
And the reason movement is going up because gamma went straight up that way.
Well, we actually eject. Think of it like we ejected all of them up. We sent all of them up.
My wrist like there's like where it ejected from, basically.
Yeah. So it's like we have a source here and we say, I'll go out and let me see which direction I'll go in. Run out. So that's that. This is probably the toughest one to understand. So let me do our next example. Let's see if CXC sent the source this direction, because that's probably what they'll do. They usually send it this direction. And last time they did this. So let's see what will happen if they had it like this, and they put the three sources here, and then they do the field in. It's going, out. That means it's coming out. Which direction they will curl? Well, you're always collecting your mark for gamma, right? If you don't understand it, anybody, make sure and collect your gamma mark. So,
Alpha will be here, and beta will be there. So in the last one, alpha was here, beta, in the magnetic alpha was here, and beta was here. And the next one is going to switch, so beta will be here, and alpha will be here.
You have to use Fleming's left hand rule, right? So don't just try to memorize it. So this is gamma. Which way alpha will turn? So alpha wants to go straight, and then is it going to turn up or is it going to turn down? Which one?
Wait, it's going on the paper.
That's out, straight out the paper, and now you need to just figure out the current.
Wait, when it go down,
This is going this way.
You need to just tell me up or down. It can only go up or down. Up, so you think alpha will go up, right? Are you agree with the up? Alpha going up? All right, so let's see. The field is coming out. The current is going this way. So yeah, up.
Okay. 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 Alright. So this is the source.
Your wrist means nothing. Up, get the up first, you get the up.
Okay, it's going up.
And then point the current.
Current going this way.
And then watch which way your thumb is pointing.
This way, this is alpha.
That's the movement. Yeah, of alpha, yes. The movement of alpha. Yeah.
Current going down.
Mm-hmm. So now what all you need to do is turn around the current now for beta, and the thumb will point down. So beta is going to go down. Isn't there a travel ban against Jamaica? This person roasting Jamaica in the chat here. Who is this? Where you from? Gamer Pro 8595. So yeah, this is us right here. What are we looking like?
I mean that type of level where I can understand you seeing you guys do it myself, but if I'm in my room by myself, I don't know.
Yeah, practice it, practice it. Let's do one more. Let's do one more. I want one dreamer way. So let's say you had the particles coming from this side.
So that's right in
Which way alpha will go?
Yo, when you go to the left, yo, when you go to the left, go up.
So she says up. Anybody agrees? Daryl Dusty man in the chat right now. But so let's do it. So it's going down, right? And which are alpha the direction of the current, so which way your thumb pointing right now? Up. Yeah. Now you said that, so you said it's gonna turn up like this. Up. The current points in the direction of alpha movement. Because it's up. Up. Point your index. YouTube, we working out something here. Point your index down, and this should point in the direction of the current. Now, your main problem is that you're not doing it in the right way. You're doing this. Everything you should practice holding it 90 degrees. Yes. And you can't move it as you move it, right? So down, yes. And this
But
goes
how
up.
do you know where the current is?
The current always moves in the direction of alpha.
And then where's the
Beta, the current will move in the opposite direction. They will put the source. So like what they will do, and all the times they brought this in the exam, they were like, oh, let's move it over here. They will say, show this is the source, this is the radioactive source, SOURCE. And they want you to show how alpha particles will move here. So you need to start off like the alpha particle is moving there and show how it will be deflected. What will be deflected. This is the right, and this is the left. It's going to be to the right.
Alpha to the right.
Mhm. It ain't looking too good. Watch. Point with me. It's pointing down. It's still down.
Okay, wait, don't, this is the thing.
Yeah, feel down. The current is coming towards me, right? Towards my chest now. So which way is your thumb pointing? You should hold it so that it looks like to you. Yeah. So therefore alpha will move like this. We can't take too long on this. We need to move. Yeah. So where will beta be going now? The other way. Well, beta is automatically just going to be the other way, but you could make beta curl a little more.
And beta curls more because why?
It's lighter.
Lighter.
It's just an electron.
Let me see if I'm really cool for this. I'm cool. Actually, I don't read. Just stop.
They ask for one more.
This is so slow.
So this is going that way, and let's say I have the source right here. Which direction will it take? These dots. And it's X's, not crosses.
Where's the source?
Source is on this side. Actually, let's put the source on this side.
Wait, where's the source?
Yeah, so you know it's going.
Okay.
Oh, you know I should have taken a picture before people left, but say what? Let's do it now.
So we can take it after.
Wait, this is going up.
That's very good.
No, watch it. We're recording to go up. So the source is wait.
So we have an alpha particle here.
Wait, this way. Wait, this way.
So then it's going to go this way?
Yeah, it's going to
So it's going to go to the right?
Yeah.
To the right.
It's going up.
Wait,
Yeah, up, that's right. Yeah, up, it's going up. Like that way? Yes. You
So,
go up and then you go
This is
down.
up, this is down, this is right, this is left. The particle can't curl to the right or left because it's moving this way, so it needs to either.
You get my point, my right side. That's all.
Alright, good. No, but that's important that you say up. So there's either up, down, left, right, out the paper or in the paper. Out the paper means it's coming towards you, in the paper means it's going into the paper. It depends. If like it depends on us on the situation. It's not possible in any of these types of situations.
Wait, so the dot means coming out, right?
Like for example, if they ask what direction is the magnetic field, you would have to say it's coming out the paper. The
Coming towards her.
well, coming towards me from like here, so.
So that means north would be behind the paper? No. North? Wait, yeah.
So let's just make sure you all did the correct thing. Coming towards me, current this way. Yes, it will go up. Beta will go down because you'll have to change the correction. The current to this way. So beta will go this way like this, and gamma goes. But that's not the last test. The next test is the field. Remember, I was talking about the electric field and I misnamed it, and I said no, I meant magnetic field. Electric field is easier, but you have to remember a little trick. So the electric field, they would put like north pole on this side, south on this side. Like so, this is the north. Sorry, electric field, and I write in north. Yes, they'll put positive charge and negative charge. Then they will let the source go like this. Well, gamma will just go straight through, right?
Wait, I didn't see this. Wait, go up.
Right. So beta will go to the positive because it's an electron.
And then alpha.
Alpha will go to the side, but make it go slower. So yeah, this one is
Beta is going to go to positive. So there's anywhere other way to like flip it something like
Yeah, they could do it. They could flip it. They could.
Just make the other on the different side.
Yeah, they could make it on a different side. They could make it this way. Put the positive here, negative there.
Where's the source?
Source might be on top or below, but you just point it. Yeah, just let the alpha go to the negative and just make sure the alpha curls less than the beta, and never curl the beta back in this scenario. It cannot turn backwards, so beta will just go to this. It doesn't turn backwards in this. It turns backwards in this example, like it will continue turning into a circle if it stayed in the field. All right.
What's an example of a question where we use this, the right hand grip?
So an example would be like to draw the magnetic field in this charge carrying conductor if the current is going up like this. Which direction will the magnetic field go? So will it go anti-clockwise or clockwise? Anti-clockwise or clockwise?
Is it going to go anti-clockwise? Is it anti-clockwise?
This is the right.
Anti-clockwise.
I can't go this way.
So this is clockwise. This way is
This
anti-clockwise.
is like the wire and the current going up and it be like this. Then if you look up from here, you go that way. Like that. So if it goes this way, then you would.
So that's the easy version. The tougher version to that question would be like to draw the field lines around these two. So these two are charge carrying conductors, and you need to draw the field lines here. How would you do this? How would you draw the field lines?
Yeah, it's so it's coming to it's on the way. That is going on. I would determine it's coming in this way. Determine. Wait, what are you trying to determine?
You're trying to draw the field lines.
Oh, it's going to the arrows.
Like how would they?
It's just an arrow.
So it's going out, it's coming up.
So let's just do one then. So if I had to use the right hand grip and draw the field lines this way, how would I do it? What does this X mean?
It's going
Thumb, right hand grip. So just draw these circles around it.
So would you go in a clockwise direction?
Yes, clockwise.
And then if it was on the
If it was up, it's going anti-clockwise.
Right. So if it was a dot, the right hand grip will be like this. So it will be anti-clockwise, like this. Making sense?
So her both is side by side. So this is going in, so it's clockwise. This is going out, so it's anti-clockwise.
Now what they could do is bring two of them right next to each other, like a dot and a cross like this, and you need to draw. So which way this was again?
This is
Clockwise.
So clockwise. And which way this one was? Anti-clockwise. So this line here will be going like that. And here it go. You understand? So this person clearly not doing physics, I hope. Clearly. So you all understand this, right?
Yes.
What other questions you'll have on this? We good? We could move forward with radioactivity.
Yes, sir.
So we went through cloud chamber. What stops it? Electric field, magnetic field, and equation for decay. The equation, yeah, let's do that. So with alpha decay, what happens in the case of alpha decay?
You add the thing.
So you produce an alpha particle. And what's the numbers here? What's the mass number? And how many? Two protons, and the charge is 2 plus, right? So let's say you had some particle minding his own business and he was like 140. What would be the product here?
100 minus 4.
This would be 96 and this would be 38.
Everybody cooking, eh? So this is the equation for alpha decay. So beta decay is actually a little weird. Yeah,
stands for like
and beta decay. I just made up these two things. So most likely it'd be some kind of uranium and some kind of more So beta decay, remember beta decay has the trans neutron in it. I just call it a trans neutron. You can see why I just think. So yeah, I made that one. So let's say we have 140. What is a beta particle? 0 mass, -1. Sorry for the charge, -1. This is really just an electron, right? But what happens? How do you get an electron here now? See if you all remember this. Yeah, from A.
Yo, you have to make this 41. You have to add 1 to the 40.
So I'm gonna add 1 to the.
And then 100 will stay the same.
Yes. So what happened for that to do this?
What happened where?
What happened with A and B? What happened? How did this happen? How this actually went up from 40? A neutron.
Neutron turned into what?
The trans neutron. So the neutron turned into a proton, and as it did that, it emitted an electron as well. So you could kind of think of a neutron as a proton and an electron together. So when the neutron decayed, it turned into a proton. So this actually went up an element on the periodic table.
You said the neutron turned to a proton.
So this one, how many neutrons was in E? 60. How many protons was in E? 40. How many neutrons in B?
59.
59. It lost the neutron that turned into a proton. So how many protons? 41. You can see it in the atomic number. The atomic number is the proton number. And one of the protons turned into one of the neutrons turned into a proton and an electron. The electron is the beta particle. And well, gamma decay is just a byproduct. So sometimes these things have plus gamma. So there's no like equation for gamma decay. So these are the equations. What else, boy? Let me just check my 12 hour with this. So here's an example of what I just said. Draw the electric field from the no, this is the electric field drawing. What is it? What is the definition of an electric field?
See, I'll just regionally means like in which something experiences and charge experience temperature and area.
Okay.
So could you differentiate?
And how would you draw this? Would you draw from positive to negative or negative to positive?
Positive to negative. And then the outer lines we got maybe.
The outer lines we just put abolish. Mm-hmm.
What is that called? Like lateral repulsion or something?
Oh yeah, so that's properties of the the waves, the field lines. So there's lateral tension between them. So one thing you must never do is let the lines touch. So as soon as the lines touch, they will immediately take away a mark. So always keep that like what we call lateral tension between them, yes.
So, sir, that electric.
That's what I'm getting. My exact. The region in which a body experiences a force due to its charge. Clean. So there's some tricks here, so let me just show you. A lightning strike is an example of electrostatic hazard. Now let me just see how quick revision. Nah, still too easy. Let's go forward. So let me see. 1, 2. Did I do? Guys, I'm just trying to find why this person writing 6, 7 over and over in my chat forward. Electricity is so huge. Right, here's we're going through some what are the questions you guys have on this?
More protons, and then the less neutrons. Use the neutron term.
That's a you guys good with this? You understand half-lives?
Yes.
Or you were making some noise on the mass defect stuff. The equal MC. Look at this. This is an example of magnetic. The source, the radioactive source, and they want you to show alpha, beta, and gamma will be affected in an electric field.
In an electric field, alpha goes to negative.
All right, and make sure the curve looks a little sharper for beta, and gamma will go straight through, right?
Wait, you know what you're
Look at there's an example of using the equations. So try to write the first beta decay equation.
Alright. This is the first beta. First beta decay. Alright, we can try this from. So atomic number element. Okay, atomic number. So atomic number 206. It tells you the atomic number. What is your PV? First decay. So it's gonna be yo. It's not.
So you started off with this one, right? Mm-hmm. You don't even need to know about them, you just need to do what you know. So how would alpha decay look here? I'm sorry, how would beta decay look? What does beta decay do?
It's gonna
So it's going to go to 83. So who is 83? Bi. And you keep this at 210, and then you put the beta particle. Or if you want, you could put the electron.
Bi 210 plus electron 0 negative.
Or you could put beta there if you want as well. Now do the next equation. Just now, I need to go on my YouTube chat and sort out what's happening here with these people.
You start with the I think so. That's like a second.
So 84.
You go to PO.
And then this value. PO. And then this would be
P.
Yeah.
So BI goes to PO?
Yes.
And this is from decay.
Plus this again. And then alpha decay.
Alpha decay. You'll be. Oh shoot. You'll be PO. Wait.
Yeah, he was getting out of hand. I had to block somebody. So you would start off with this new one, BI 83 210. Then it will go up again, right? So 84. And who's 84? PO 210 plus another electron out. And then what would the last equation look like? Somebody's asking me to do half-life, please. So I'll do an example. No, you have to start. Yeah, so you're starting off with the PO 84 210. And what does alpha? This is alpha decay now and not beta. No, it's gonna come back down. 82, right? That's the whole plan. That was the plan all along. You started off with lead and ended back up with lead.
So how much marks was this number?
Like 6 or something? Yeah, 6 marks.
6 marks?
Yeah.
Are you happy?
You are. So this is.
206. Okay. This takes us.
And then you have to put your alpha particle here or helium nuclei.
So you start off with they start off because I told you the question like wait, the nuclear equation that we got in the formation of stable from PB. Okay.
So you started off at this, it's like you went up, and then you come back down. And the whole point of radioactivity is that the atoms do this to try and get more stable. So this one was unstable, but this one here is stable.
So it has to be a beta decay occurred first?
So not all the time. Sometimes it will just do an alpha decay, sometimes it will do a beta, then an alpha. This is just a random thing, right? Okay, so this is a basic form of it. They actually give you the mass defect. The mass of the reactants minus the mass of the products. And you usually work it out in atomic mass units. You all remember that from chemistry, the U. So you usually, you'll listen to this, you usually have to record this. Yeah, so you usually, the student will have to record this. But they gave you it in this example. So E equal mc squared. The only thing is you can't just throw this m in there. You have to multiply this by 1.66 times 10 to the negative 27. They will give you that number. Yeah. So one atomic mass unit is this. So E is going to be 1.66 times 10 to the negative 27, and you multiply this by 0.318, and then you multiply by the speed of light. Don't forget the square, it's a common mistake. Squared, C squared, and you get your answer.
So you're saying it's 0.3018.
Oh, sorry, my bad. Yeah, 0 should be there.
Wait, so you're saying this is the case where they give you the change in mass, but then the other times you have to find it?
Most of the other times you have to work it out. So like this diagram is wrong, right? It never turns backward in this type of field. It will just go like this. Yes, always. But it's 3 times 10 to the power of 8. You can memorize that. 3 times 10 to the power of 8. So here's an example of the half-life stuff. I did this with my class earlier in a crash course. So you have to like plot the graph. This is like a worst case scenario. you plot the graph with the time. So you end up with something like this, and then you work out the half-life. You all know how to work out the half-life, right? So you read this.
You split the graph in half, and you split that slice in half. So it's like 80, you move 40, and then 40 minus 80.
Did you see class?
Yes, bro.
For one half,
So the graph for this came out a little jokey. So it should usually be more like a curve. It should usually be more like a curve like this, right? And watch what happens. You would read off, okay, this is activity. So this on this axis you'll usually have activity or disintegration per second or something with becquerels or something like that. Becquerels.
That's activity of the.
Yeah, that is some unit for activity. You don't need to go too deep in CSEC physics. So this is 70. What is half of 70? 35. So this, when I touch the graph and come down here, that will be the half-life. So like this was 1.3 and this is 35 was 3. So the half-life is 3 minus 1.3 minutes.
Wait, what do we do here?
Let me give you an example. So this is the graph version. How do I do this again? No.
Yeah.
It's the easiest graph. This is the easiest graph we're gonna get. It's the easiest graph. It's the easiest graph we're gonna get.
All right, watch this. See if y'all can figure it out here. I'm gonna come up with one brand new, right? So let's say this is T, this is activity, and we have a situation like this. I hope my graph makes sense. Probably I should start from here. So I have this graph cooking up here, people. So I have 1, 2, 3, 4, 5, 6 time, hours. And let's say the activity here started 10, 20, 30, 40, 50, 60, 70. Okay, so what's the half-life of this?
So, we divide the 75.
35.
And then 35 divided by 2.
Yo, start over, bro.
So this is the activity. This is activity 1. So when it was 70, the time was 0 seconds. So what is half-life? Half-life is the time taken for the activity to drop to half. So half of 70 is 35. So 35 meets the graph at 2. So that's the half-life there. 2 minus 0 is 2 minus 0 is 2.
Oh, right.
But it's not seconds, it's actually, you have to watch this. This is one of the tricks. You have to watch what they have here. So it's 2 hours. Now there's another way. When this comes, if you do this, let's say this was like 4 marks, you would only get 3 out of the 4 marks. Why? You have to do it again. So you have to start like maybe with 40. Read off what 40 is giving you. 40 is giving me what? 1.6?
Choose a random one.
You can choose a random one.
Starting at 40 would be the new activity that we started from. Okay.
And then 20 went to.
Divide by 25.
You could I can do it with 35.
How many of them?
Yeah, but usually I pick nice numbers. 17.5 I kind of this. No, you don't need to. Yeah, most students don't know that.
Oh, you just have to keep going down.
Yeah, so you get 3.6. So 3.6 minus 1.6 is another 2 hours.
Yeah, so 2
And 2 plus 2. Yeah. So in the example that we did earlier, where is it? In this example, when they worked out the 2 half-lives, they got 1.7 and 1.5, so the half-life was 1.6, right? Add up the 2 and divide. So you have to remember to do that if it comes in a question 1.
That's all this question will ask us to do? This half-life thing?
No, well, this is worst case scenario half-life where you have the graph. Yeah, probably. So half-lives usually come like most of the times they'll come where you have to like work it out. Find how many half-lives. Okay, let's say the activity of a sample was 16, whatever. And then after I think I have a sample
She
here.
said it before. She said this before.
If you wanted to be in the live, you could have just come here, you know. Let me see if I find a question where it's tested enough. Man. So yeah, listen how the half-life thing will come. So yeah, that's the clicky thing. So the GM thing. So let's say the activity was 16, let's say some random number. You don't really need to know about the number. And then after 360 minutes, the activity fell to 2. What is the half-life? So they want, but that's not the answer. The answer is what is the half-life? What? You're listening, you're paying attention. So the activity started off at 16 and then it went down to 2. The time it took to do was 360 minutes. What is the value of one half-life?
15 to 8 to 4.
So that's what you'd be trying to
That'll be
find.
what, 3 half-lives?
So you have to be careful with how you work in all the half-lives. I always advise at this level to work it out manually. 16 to 8, 8 to 4, and 4 to 2. Because people work it out mentally, they will get 4, like what you got, but it's actually 3.
So 6.
But
So
yeah.
you can do it 3 times.
So there's 3 halves. So 3 half-lives pass, and 3 half-lives took 360 minutes. So how much will one half-life take? 3 into 360 is 120. See, Kirsten had the answer a long time, eh?
Like we know. Like we had
Big up Kirsten. So 120. All right. Y'all understand that?
Yes,
Power math.
Sure.
All right. So what other topic in physics y'all want to know about?
Hold on. We have to go on this list. What do you say to do? Also, rectification.
Rectification. You want to talk about rectification?
Yeah.
Oh, yes.
So what comes on rectification? Firstly, what is rectification? AC to DC.
I like turn some of the load on the splitting the load and stuff like that. Alright.
Are there any equations in this topic? Like you have maths and maths? Not really. So there's no equations really. So in this part of, if a question come on this, they may ask you some stuff on peak voltage and RMS voltage. So peak voltage is the value from the neutral position to the top. So like let's say this is 6 volts. So the peak voltage is 6 volts. But if they ask for the peak to peak voltage, that's 6 plus 6, which will be 12. Well, 6 plus the positive version of that, right? The RMS voltage is, well, this isn't always at 6 all the time, right? It's only hitting 6 every now and then. So the average voltage that this is carrying is found by multiplying the peak voltage by a number. You all know what the number is? So you have V peak and V RMS. So the V RMS is very simple. V peak is root 2 times V RMS. And that's it. It's nothing
V what is equal?
the peak voltage is the square root of 2. We call it the root mean squared. That's what RMS stand for. Root mean squared. The square root of 2 times V RMS.
How we get the square root of 2 like that? Did you know that?
Yeah, no, you should just know that. That's just the constant.
Oh, you just know that.
Wait, what is RMS stand for? Yeah, what's the square?
Root mean
Root
squared.
mean squared. And that root mean squared is like the
Wait, so what is it? So the square doesn't always look so.
Is he Kirsten have any? So let's say V peak is 6, VP is 6 V, and you're trying to find VRMS. Well, you just put 6 is equal to root 2 VRMS. So VRMS would be 6 over root 2.
VRMS mean what again?
That's like
Wait,
root mean squared.
But VRMS is what?
That's like if you imagined that this voltage was acting as a direct current instead of AC, what would it be hitting? It wouldn't be hitting 6 all the time because it's only touching 6 every now and then. So this is like the average effect of the volts. But now they would not say that. But you just really need to know this formula. So 6 over root 2 and whatever that is, I don't know what it is.
So what's if they ask you for the peak to peak voltage and you say it's 12? You can apply the formula to the 12, this to the 12? Like to find a VRMS? If they're supposed to find a peak to peak voltage.
No, well, you just add the 6 and the 6, that has nothing to do with VRMS.
Okay.
You usually ask about peak to peak voltage. Very rarely I would see anything about this VRMS. I doubt it will show up. So yeah, we are talking about rectification. Rectification is, oh geez, turning AC to DC, right? What do you use to make this happen? We use a diode, semiconductor diode, right? So if I send AC supply through a diode, we will rectify the current. So the AC supply would have been like this. What would the DC supply look like? It will eliminate all the yeah.
So it wouldn't go in the
So what about the
How did it this it doesn't flow in the low.
So the diode restricts the flow of current in one, allows the flow of that current only in one direction.
So you want to form a diverse bias.
No. So if, however, they decided to put the diode in the opposite direction, the top halves will get cut off there, and just the bottom pieces will be there.
So the point where the current is turning in the diode.
This is pointing the direction that you allow the current to flow through. So we'll consider this, since it's pointing forward, as the positive direction. So that's this is called a special type of rectification. What type of rectification? Half wave.
So we don't need to know No, 4 diodes.
Right. So you don't need to draw the 4 diodes set up for full wave rectification. You should just should know that there's something that exists called full wave rectification, which would take this and flip it back in this direction. So you'll end up with this scenario. And if you ever wanted to smooth, what they call smooth a capacitor, use a capacitor for smoothing.
Random facts I know, but I can't.
Yeah.
The whole syllabus she knows. The whole syllabus she knows.
You're gonna say this will be the camera.
The whole syllabus she knows. That's a lie.
So you don't need to know much about half wave rectification. What other things comes with rectification?
No, that was I'm talking about section here.
Yeah, so feel free to ask any questions now.
Just go through the syllabus.
Wait, what is it saying? Conduct an activity to demonstrate the random nature of radioactivity. Is
You know, like the points.
Yeah, we're flipping the coins and
You
or
have-
dice.
You have 2 waves and optics.
That's the same thing we are just doing. So like,
Nothing's worse than these.
no, that's easy. So like you have the dice, the 6-sided dice. You have 100 dice and you flip it and you remove all the dice that has the number 6 on it, and you keep removing it every turn and you flip again. Or if you're using coins,
What?
Let's say you have a 100. You're all overthinking it. It's very simple.
We did it in the lab.
We did it, guys.
We did it.
It's guaranteed that you did this in the lab because it's a, it's a
100%.
Remember we flipped the coins.
So most likely you use coins and you flip the coins and you remove all the coins with heads or tails or whatever it is.
Oh yeah.
Yeah, I remember that.
Wait,
I remember.
refresh me. And that was 20 what?
I remember.
So what will happen is after your first pass, you'll go from 100 points to maybe like 52 or something.
Yeah.
In a perfect world, you'll go to 50. And then it will half again. You'll go to 25 or 27. Then it half again. You'll get like maybe 13. And then you draw this on the graph, the passes. So you put like the 0 was 100, 2 was 52, 3 was, and you connect this and it will show this curve. What is the type of curve called? It's called EXPONE exponential decay.
Wait, the stuff on the x-axis is what's it?
Each pass, which kind of represents the time passing. So it's showing exponential decay. Now this one is obvious because the half-life will be every flip. Every flip it should be getting half the amount. If you do the one of the dice, it takes a little longer for you to see the half-life process coming out because you only
keep looking at the
no, because the dice you're just removing the 6. You're just only removing the ones with 6. So it's not like you're taking out half one time. Yeah, more will stay. So this will have a longer half-life.
Oh, 6 dice.
Okay.
Yeah. All right. Any other topic? That's just theory. That has nothing to do with anything.
Wow.
You just need to know the color.
There's no color.
Yeah, of light, neutral. Yeah. Light is brown, yes. I don't know why not right.
What makes one name? Black?
Wait, you can figure this out under the
Blue? Which one?
Blue, yeah. This is brown.
Blue is like.
This is yellow, green, I believe. This changed like 3 times since I doing CXE. So it'll be hard for me to remember blue.
How is it going?
So you can review this. Yeah, so what other topic?
waves. Oh, that's harder than waves. So did that.
Okay.
So which part of optics?
You don't have to do the image. You can swap the image.
So there are 2 types of lens. What are the 2 types of lens you need to know in optics? So there's convex or biconvex, and this type of lens is called what? Concave. So the thing that you all are talking about that most students struggle with is just being able to draw the image. So that's the worst case scenario. Like they set up the lens and then you have to draw the image. So how do you do that? There's 2 points you need to know. Focal point and who?
The
Optical center. Yeah, but I wasn't really talking about that. There's the focal point and then there's 2F. So then there's F and then there's 2F here. So there's some key lines that help you like immediately draw this no matter where it goes. So like let's say I have this, the object here. Let me ask you, you're hearing that background noise? You're hearing that background music? So the key lines are, if we have a line that runs parallel, what will happen to that line? It will go through the focal point. So that's one. And if one, my focal point in a kind of not too good spot here. We're begging waves. Waves in the chat.
Like transverse waves.
So this line will go through the focal point and then end up being what? Parallel. So that's your image there. And there's also a line that will go straight through the optical center.
What's this going here?
Hmm?
What is this going there?
This is going through the focal point on this side.
I thought we just did one from here and one from here.
You can do that one as well, one through the
So
center.
just do one of them.
Do two. You have to do two. It have to intersect.
So I can choose to do this one, I can do this one from here.
Yeah.
Okay.
What's the symbol again? Which one has the thing on the top like the straight line and then?
So let me see if I can find. Let me see if I can find.
Yeah, which one is it?
This is the top.
Somebody saying come to immaculate next.
No, sir.
Yeah, so this is like an example of what's happening here. Let's watch. So if it's on the, guys, look at this. If it's on the focal point, the image forms at infinity.
Wait, stop. Leave all of this. What's this?
Infinity.
So this is the focal point.
The principal axis is this dotted line.
Mhm.
On the focal point. This is the lens. What kind of angle is this?
So I want to make a point, but where can I do that? Labels, object one, focal point. I want to add in the next focal point. Am I allowed to do that? So yeah, like if I could actually, what is the equation that follows this part of the syllabus?
1 over F.
What is the equation called? What is that equation for? Yeah, lens formula. Right? So that I just Nassus.
Lens is not. I'm confusing where it was. Oh, lens is not. Lens is electro stuff. Lens is talking about the direction of light.
That's not. Let me see. Was she correct? Lens with the Z. All right. So lens with the Z opposes the
Yeah, like
Yeah,
you oppose the EMF that created something.
Lock into this. Lock into this. You'll answer this, right? So if the object is on 2F, the image forms at infinity. You have to know that. Eh? So, and you need to know like examples of this, like where this would be used. So this would be used in things like a spotlight, right? So so if the object is between F and 2F, hold on. If the object is between F and 2F, the image forms on the next side from F to infinity.
Oh wait, I know this.
Of course.
I know this, but I just don't.
Right?
I have to draw it.
Listen. If the image is exactly on 2F, 2 times the focal length, this other side here is also 2F then.
Yeah.
Now if the did I say image? If the object is on 2F, the image is on 2F. If the object is before 2F or after, between 2F and infinity, then the image will form between F and 2F. So you can never get the image really before F. To get the image on F, it means the object is at infinity or really far away. So you can check your notes and see examples of
You
this.
do the same thing if you have the object. If you have the
Or
object.
research online.
If you have the object between the optical center and F, then what is it gonna do?
Oh yeah, so that's a special case. So what do you say? What happens to the object when it's between F and the optical center?
Oh, yeah, that's the observer.
That's a virtual image, yes. So every time you talk about image and object in this part of the syllabus, you have to be able to describe it. So you have to be able to describe what type of image it is, the size of the image, and whether it's upright. So for example,
So that would be, so it's virtual and
why? And they can't be doing the violence on the street.
Mosquito was on his shoulder.
I'm mosquito. So between F and 2F, watch the image. How would you describe this image? It's real, inverted, and enlarged, right? So if the image if the object is
Hear that chat? You know what's happening.
Kristen, the way you know this note.
Chat out here.
Right now it's 8 o'clock in Jamaica, so it's around 9 p.m. in most of the Caribbean. So if the object is beyond 2F, what happens to the image now? What is it?
It's diminished.
Diminished.
Inverted.
Right. And in this case, if it's here, what is the
It's
image?
virtual, enlarged, and
What's this word? Starts with U.
U.
Upright. So it's upright. Right. So yeah, that's what would come on this. So, but most of the times that they bring this, they'll just bring like one thing where they ask you if the object is there, describe the image and where it would be. You get 3 marks, and then they will ask you a question like maybe say the image is at 240 cm from the optical sector, and the object focal length, they'll probably give you focal length and then ask you. And F is equal to like, I don't know, I could just make up something. Let's say, let's just say F is 90 cm. So find U. So go ahead and find U here, everybody.
1 over 90. 1 over 90 equals plus 1 over 240.
So who's gonna do
So V is equal to this. So you have 1 over F is equal to 1 over U plus 1 over V.
What are you trying to do here again? F is. Okay.
That's what you're trying to find.
Oh.
So 1 over F is 1 over 90 is equal to 1 over U plus 1 over 240. So then 1 over 90 minus 1 over 240. And how much you get? 1 over 140 for this year. And don't forget to, wait, that's 1 over U, so we're not done yet, sorry. So then U is equal to 144 cm. Yeah, they invert it. If it's a fraction, you'll just invert it and divide and find it out.
So we just invert it.
So you all said you know the resistance thing. Like if you wanted to, there's this circuit and the voltage here, let's say it's 9 volts, and it's going around the circuit. And and let's say this is 3 ohms, 4 ohms, 5 ohms. Actually, let's make this 6. So, okay, so they want the value of the current flowing through the circuit.
Alright, this is a parallel, so current's gonna split across the each. Voltage is the same.
So this is VT. They want like the total current, like the current that's flowing through this part, this component here. What would be the value on the ammeter here?
Bro, it's gonna be the same going into a 5.
Wait, no, because that's coming.
So the first thing you need to do is find the total resistance in the circuit. Because you want to use V is equal to IR. So you'll have to find RT. So how are you going to find RT now? Okay, and how are you doing that?
So this is for the parallel,
And add it to the 5 one, right?
yeah.
So how do you find the voltage in the parallel path? So you're going to find,
Like R1 times R2 over R1.
let's call this R1, R2, R3. So we're going to find the resistance in parallel and add it to R1.
It's
So
gonna be 2.4.
So you say 1 over Rp, the total parallel is 1 over 6 plus 1 over 4. Agreed? So this is 12, 6 goes into that 2 times, so 2 and 3, 5 12s, 12 over 5. And the n is RP. You'll understand why I did there, right? I just found it and flip it back because this is 1 over RP. Are they paying attention?
Yeah.
Yes, they're paying so much attention.
Tell me I got this. So then this is 2.4, right?
2.4, yes. 2.4.
Did you
add it to the
Yeah, chat, you all hear that? So this is 2.4 ohms. So this will represent, it's important to note that this is 4 ohms and this is 6 ohms, but this is less. It's like the more space you have, the less the resistance. And that's something they could ask you. How do you lower the resistance? If the wire,
How do you lower it more space? The question, and I said, the question asked, which circuit would allow lower resistance to or something like that? Oh, yeah. I said, I don't understand why. I didn't understand why.
so while you were getting the 2.4, Kristen was getting the answer, Kristen, at the end.
How do you know when you're so much space is space? Like, that's why.
So RT is 2.4
So
plus.
what's logic behind that? That why it's reduced, you're saying, oh, so more space, it's...
Like if you have 4 cars to drive down a road, but the road has 2 lanes.
What is it, 4 cars to what? Yeah?
4 cars trying to drive down the road and it has 2 lanes. But if you have to go on a highway like 4 lanes compared to 2 lanes, it'll have less traffic. So the wire.
I like that.
Yeah. So the wire, you can think of the electrons as they trying to make their way downtown here. And if it's a really thin wire, they'll have to force through this tiny space. This is why like filament bulbs use thin tungsten wire so that as the electrons go through there, it's the light bulb has tungsten.
This type of wire.
The filament bulb. Well, oh yeah, you wouldn't really know about that. But I used to be in my days all the time. So all the lights were light bulbs, like literal light bulbs, not these fluorescent lights or anything.
So if it's thin, then that means there's gonna be more resistance.
And heat will cause it to glow.
And then there'll be like less current.
Well, there's a relationship between the current and voltage, V equal IR.
Obstruct like.
But the heat causes the glow, and that makes light.
Okay. So that's why you say that the 2 factors that can affect like the resistance of a wire is the length and the thickness of the wire.
Right. So if you make it longer, what happens? This electron had to go through all this length, which is why, how does a variable resistor work? Or what's the next name for? Yeah. You all see one in the lab, right? It's like a little block, so, and then you have a whole bunch of wires going down, so a whole bunch of wires going down. And then there's a little knob on top that you just move. You know what I'm talking about? And this is connected. Yeah.
You know that one time.
Yeah. So you move this. And what is happening is the electron will have to go through this in all this, and the more wire that the more you push this back is the higher the resistance you make in a variable resistor. That's a variable resistor there. So yeah, length of wire, if the wire gets longer, the resistance goes up. If the wire is shorter, less resistance, or if the wire is thicker, less resistance. And the other thing that affects resistance is temperature. So what do you think will happen to temperature? If you raise the temperature, will the resistance go up or down?
No. Because if it's like cold, like they can't move or so. Yeah.
Correct.
Right?
So if you
Yes.
Kristen get up before me?
So remember, these molecules inside here are vibrating. So if the electrons are trying to pass through here and it's hot, they'll be vibrating more, so it'll be tougher. So like superconductors are chilled, really cold. So the colder you make something is you send up the resistance up really high. Really low, sorry, you send the resistance down really low.
Wait, you said we call the resistance low?
Yes.
Wait, so longer wire.
That's what I said.
Oh, we probably.
No, you said the correct
That's
thing.
what you said.
Yeah.
That's what you said. So longer is also less.
So you're saying if it's colder,
Longer is more resistance.
so if it's colder, they can move more like uniformly?
You can move freely because the molecules are not vibrating, so the electrons are free to go through. So colder, less resistance.
Did we talk about the action of the
Cause
AC
and less
generator?
resistance.
Action of the AC generator. We
This
talked
is
about the AC
explain the
generator.
action of the AC generator.
Well, we went through the AC generator. So which is 2.4 plus 5, so this is 7.4 ohms. And then you use the 7.4 in V equal IR to find R. V is equal to IR. So remember, resistance in series, you just add. So once we found that this was 2.4, you just add it to the 5, we get 7.4. So I is going to be equal to 9 over 7.4, which is how much? Kristen say 1.22 amps.
Yo, keep that built in the AI in their keyboards.
All right, ask another topic.
Simple activities demonstrate and induce EMF, coil and magnets to coils.
Yeah, so what happens in that question is that there will be a coil like this, and there'll be a galvanometer here, and they'll ask you which way it will deflect. No, yeah, well, kinda. Which way it will deflect if the north
Oh, yeah, I know.
goes through there. If the north go, if it goes this way, which way will it deflect? Which way will it do
So
so?
putting a magnet in here. So, oh my gosh.
So the I know this one.
Yo, I know this is what I just don't
We did it actually.
Wait, what's that?
Yeah, we did this one.
We
Yeah, you put
Yeah, she showed us, but did I
Yeah,
understand?
she did show us.
Of course I understood.
So if you put the south pole in the
You're inducing a north pole. No,
No,
you
it's a
can't.
south pole. Like
If you put
if you put
the
south pole towards it, then a south pole is going to be created in front of the south pole.
Hold on, there's already
Bro,
this.
that's Lenz. That's Lenz. Lenz is the guy that said that if you put the south pole, there's current's gonna flow in a way that induces a south pole right there, so it's gonna repel. I think, right?
Right. But it's going from north to south. So I really just look at the north. So if the north is moving this way, the current will want to flow in the opposite direction.
So it's now
You're moving the magnet. You're moving the magnet. The direction of the north pole and you're using that way. This is the
Hold on.
south pole, this is north pole. So look at this. The north is going that way.
So yeah, like if the north was going into this, the current would want to flow in a way to oppose this. So this would be flowing this way, so the galvanometer will turn like this.
yeah.
North is going this way, and you're saying current's gonna want to oppose it.
So it's gonna create north pole on the other side. If the north pole is going away, the north pole will create. I'm confused.
Well, to find the north pole, you could just go with the current to find it. This one is not about where it will create the north pole really. This is in which direction the galvanometer will turn. So the question that you're talking about, where they'll ask where the north pole is when they have. Just make sure this using in my so they'll have the positive here. Oh gosh. And you need to figure out where is the north and the south. So that's that question. So can you figure out where the north and the south is here? So like this is positive, this is negative. So this is going through here. There's a way to use your right hand grip to figure this out easily. So just do your fingers which way the current is going, and your thumb will point towards the north. So this is the north, this is the south.
So current,
If the current is going this way, current goes back to south. So that's not. Oh, you're right.
wait, what's it telling us now? What is it?
Going here.
Take the current, find which direction it's going,
Yeah.
This represents north pole.
and then use your fingers to curl in the direction the current is going. It's curling clockwise. So you go this way, and you point like this.
And then no north that way. That's it. That's how to do.
That's it. That's a shortcut.
What's the one before that? The question before that? Oh, putting the magnet in there.
The question before that is the north. I just focus on the north. So as the north is going in, the current will want to go in a direction that is opposing this. Now it's cutting the magnetic flux, and you could use Fleming's right-hand rule and figure out everything. But the shortcut I just do is with the north going in, it will want to oppose. So therefore you can figure out everything from that. If the south is going in, it will want to go with the south. So this will go this way. So south going, yeah,
So if that magnet was flipped, you have an element of movement.
yes.
Wait.
This is a second.
So when you put the south pole, it's gonna the south pole is gonna be on the same side of the south pole. Like
So
it's not on the same side. But
what's the logic?
I need to double check this again. Let's see here, north going in.
What's the logic behind the current wanting to go to the south?
The north pole is on the other side. So the south pole are facing.
No, it's working, it's working.
What's the logic behind the current wanting to go to the south and not going to the east?
With this, well, when we do the field lines, remember when we was doing the field lines with generator, if we have the magnetic field going from north to south, we point our finger this way. If it's going from north to south this way, you point your finger that way, and that's going to cause the current to just flip direction. So
this is using a right hand.
this is using the right hand. So it matters which way is north and which way is south. Decay get evicted from that position. All right, any other questions?
Yo,
Pass paper.
can I get that one by just reading the consensus?
You don't have time. No, when I look at the
No, you need
concept,
to practice the questions
you
as well.
can't read that in the time.
How much past papers do I
You want
need?
to finish it?
I would say maybe like 3.
How much past paper you said? How much to go?
40? Why are you asking me?
I didn't already said. I didn't.
Run through 3. But you might need like about 5 or 6. You will need a little more. Somebody said moments and waves. So let's talk about moments. What do you all know about moments?
Moment of what?
Moment is like the turn that direct off by like
So what's the unit of moments then?
Newton.
Very good.
I need 5 past papers.
No, that's moment. Yo, it's moment. Oh, you know what kills me? Moments. And they say it's like a uniform thing, so that the way it's in the center, not like you know. I did that question. Yeah, I did that question wrong one time. It was like, what's the
different types?
Yes, first class, second class, third class.
Never gonna question.
No, wait, the first class we were the seesaw, no?
Yeah, the first class is the seesaw.
Second class is like a door?
No.
One is a bicep is third class.
All right, let's do a simple question on moments. So let's say there's this cat, and this cat is 500 kilograms, and it's a certain distance away from this X, and the whole thing is 5 meters. Let's say it's 5 meters. So, and the mass of the bridge, they'll say this is uniform mass of 120 kilograms. Find all right, let me give you this. Let's say this is 2.0. Find the tension. Of course, there's a high chance. Find find the most likely find the value of T1 and T2. The value of T1 and T2. Or F1 and F2. They will call it a force, F1 and F2.
Okay. Your T1 and T2 has to be equal to what that car is pushing down on.
Wow, really?
Don't be just saying like I'm not trying.
Oh,
Yeah, just give her because she.
All right, yeah, this is a really easy one, so you have to.
Your daughter like. Ask him to send it in your
So yeah, what would be the value of F1 and F2?
So, yeah, we said this is CWM equals CW.
7 max.
Wait, you know the mass of the car?
Yes, it's 500. So 500 is here, and it's O on this side, so it's going to go down, and it's going to turn it. This is anti-clockwise.
Uniform mass of
5,000 times 3.
Wait, 120 kg is the mass of this block then?
Yes.
What's it to do?
120.
Mass of F2.
Wait, that's not the mass of F2. It's just
What's
the
the
mass of
because you think oh wait.
minus 0.5. Wait.
why you minus?
Yeah, that's mine.
39. I need a camera. I'm not doing this. I'm not visualizing this.
Wait, so 0. So this stops at 3.
Where's it from?
All right, let's see Samantha and Christina and them can get out too. Nah.
Bro, I got something.
See if y'all can get this out, chat.
If the car, the weight of the car is what you're talking. If the weight, wait, what's that?
Yeah, I'm okay. I'm just tired.
Where is it?
So at moments, there's always two things to remember for the static equilibrium. What are the two things to remember?
That's translation.
What are you talking about?
Bro, remember their translation?
I can't remember herself.
So for static equilibrium, what are the two things? Right. So the total anti-clockwise moments is equal to the total clockwise moments, and that's one. And what's the next thing? Right. And what's the better way to write that? The sum of all the forces in the system is equal to 0. Net, yeah. Net forces. However, in the question that you'll get for CXE, what you will be seeing is upward force equal downward force. For like when it's time to work it out. You write this if they ask for the definitions for static equilibrium, but when it's time to work it out, you'll say upward force equals downward force. Right, so how are we going to work out this now? To work out these questions, you always take moments about a point. So how do we? So we can take moments about which point? Let's take moments about F2. F2. It doesn't matter, F1, F2 don't matter. But F2, since I have a distance from F2 here. So if we take moments about F2, we'd eliminate a force. Which force will we eliminate? No. F2, because F2 is only 0. So, and then you write total anti-clockwise moments equal total clockwise moments. So the anti-clockwise moments would be the stuff that's sending it anti-clockwise. Can you give me an example of a force that's producing anti-clockwise moments here? The cart. And what the mass of the cat is 500 kilograms. So what's the force? So the force is 5,000, right? So you multiply by 10, right? Everybody know that trick by now. So you write that out properly in the exam. So we have 5,000 multiplied by what? Because remember, moments is F by 2. And then what else? Are there any other, sorry, this is anti-clockwise. Are there any other anti-clockwise forces? Do you see any other anti-clockwise forces? Yes, there's another.
The mass of the thing.
Yeah, the mass of the bridge itself, or the plank. So, and where is that acting? From the center since it's uniform. So we have 120 with extra 0 newtons going on here since it's 120 kilograms. And then what's the distance?
Wait, go again, say that again.
It's 120 kilograms, so F is equal to MA or W is equal to mg.
Since it's uniform, that means like it's active on the center. So it's also 120.
Right? So you get that?
No, the uniform part in the center.
If it's uniform, it's acting in the center, so what's the distance? Then you can't do that. But you can get non-uniform, but they wouldn't access something like this. So this is going to be 2.5, right? So we're going to get, and what is this equal to? What is the clockwise moments now? F1 times 5, right? Because this is actually pushing it up, keeping it up. So F1 times 5. And then you work out all of this.
2600.
How much is the left hand side working out to be?
13,000.
So then F1 is 13,000 divided by 5, which is?
2600.
And what's the fast way to now figure out F2? Nice, very good. So since we figured out this was, how much you said? 2,600 newtons. We can figure out this one. Because this is 5,000, 1,200.
It's going to be 2,400?
No, it wouldn't be. It has to be more.
More?
Mm-hmm.
If this is 2,600.
What's the total downward force? 1,200 plus 5.
Oh, jeez.
So the force is downward.
This is what? 6,200.
Right. And what's the upward forces? So far we just have this, so what's the missing? F2. So that's F2 plus F1 equal that.
Minus 2,600. Yeah. Which means 2,600? 3,600?
You fall in asleep, Baber? 2600.
No, sir.
So how much you'll get?
3,600? Is that right?
36, right? Yes. Notice how this one is a little more. Why is this one more? Because the cat is more on this side, right? So 3,600. So that's like an example of how they bring moments.
That's the hardest we get.
About. But all you need to do is stop and think. It's usually something like this you have to do. It's a combination of the both things. The upward force equals downward force and moments.
When you get like an arm movement that's more complicated, can you just simplify it and draw it?
Yeah.
The arm?
Yeah, like just
Just
draw it.
just anything that's complicated.
Yeah, just draw the line.
Just draw a line.
You don't need to put their mind.
Questions? We're wrapping up in a little bit.
Sarah, I have a question.
Oh yeah, let me see.
It's a
Kirsten needed some help on this one, yes. She needed help.
On this question.
Define the term half-life. So we already know half-life. So the same thorium has a half-life of 24 days and undergoes beta decay. Calculate the time, it will take 10 grams. But we just did a question like this. This person wasn't paying attention. 1.25 grams. So the beta decay and all of that is just distractors. So 10 grams to 1.25 grams. and it has a half-life of 24 days. So how long would it take for that to
It's
happen?
gonna go to 10 to 5 to
Mm-hmm.
1.5 to 1.25.
divided by 2,
So how many half-lives?
5,
3.
Yeah, 3.
Right, so half-lives pass equal 3 half-lives. And then the time would be, no, not divide this time.
It says each half.
They gave us the half-life this time. They didn't give us the total time. So if they gave us the half-life as 24 and it took 3 half-lives, the total time would be 24 times 3, which is 72 days.
Oh my gosh,
All right,
sir.
anybody have a next question?
Sir, nothing about the Geiger Mars then experiment something, because I can't wait.
So like, we have to know about
The Geiger and the
Mhm,
Rutherford
yeah, so you-
furnace.
So this is what will, and that comes very regular. So what you have to know about that is how to draw it. Like just a quick idea of how to draw it and label some of the things. So you have this source here. And what is this?
The aluminum.
No, not aluminum.
Oh my gosh, this is the
It's a type of foil, something foil.
gold foil.
Why is it gold foil?
It's gold foil because it's reflection. I know. Gold, I can't get it, bro.
Gold has a higher atomic mass, so you get higher
What?
feedback. Gold has a higher atomic mass, so you get higher feedback.
Yeah, but that's a real,
That's what I'm my book.
it's real scientific. You need to see it in a nice layman too.
Layman term.
Also, hers is more
Gold
sensitive.
is good.
Also, I'm just.
Yeah.
You got it there. He said gold is good.
There's two reasons. It's very thin. Are they tired? They can't be more tired than me. There's two reasons. It's some kind of micrometers. Yeah, like a 2-3 micrometers. It's very thin.
Okay.
What we know about metals? What is a property of metal that can?
Shiny.
It's shiny.
Shiny.
Malleable.
That's it. Malleable.
So
So we can. So one of the reasons why it's gold is because it's malleable. So we can make it into a very thin form. And the other reason is why it's based off of our reason. Well, that's another reason actually. Gold is, what is gold famous for? Gold is inert. It doesn't react with anything. So we can just use gold and we can expect that this is only gold. So we know that this is only gold here, so it's inert. And another reason is it has a high atomic number. High atomic number means that it has a pretty large nucleus and lots of space in the
you
electrons.
can actually observe the.
So you can see what's happening. So what is the type of source that we use here? What is the alpha? We use alpha. So the alpha consists of, what is alpha? Alpha is really
Positive.
it's positive, but it's a helium nuclei. I think you said that earlier. Helium nuclei. And it just send you from behind from me? 2, 4. Do I need to remove you from behind?
Sir, I don't know, sir.
Okay. So this is alpha. It's going here. And the alpha is hitting the gold foil. And there's 2 things that's going to happen that I need to talk about. One is that you'll have some deflections and some reflecting back. Oh, by the way, what is this chemical? Either it's coated all around or it's on the detector here. What is that called? You should know the name. Zinc sulfide. So you should know that. So it's going to be reflecting back. Some is reflected all the way back. Some is deflected, but most go straight through, undeviated. So that's the 2 observations. Most go straight through, and some deflect back. Some deflect at an angle. So that's 2 observations, and the question is going to come here. I have to like maybe label something here. That's gold foil. That's zinc sulfide. Whatever. State the 2 observations they notice, and then they'll ask you what those 2 observations mean.
It means that there's like a component mainly empty space.
Right. So that's since most go straight through, most of the atom is empty space. That's one. Linking that is just mass. That's what they ask all the time. And the deflection is the next observation. What does that mean? Yeah, but you need to use some adjectives when you say that, right?
So they're
So what are the observations? Most go straight through, right? And that is linked to most of the atom is empty space. Yeah, this is Geiger Maths experiment. And the next observation was deflections. And some reflected back. When you say some reflected back, you need to say some reflected back at high speeds. Right? So you get some deflections and some reflected back at high speeds. And this means what? You're saying? Right. So just use some adjectives when you say that, right? Has a dense positive, a small dense positive charged nucleus. So in other words, you're painting the picture of the atom, a small dense positively charged, and most of it is just empty space. Very important. This comes regularly, like once every 3 times.
Once every 3 times? Do you
Mhm.
think this will be one of those times?
It could happen.
Bro, remember them don't like we.
Bro, please just give us all the first photos.
So why not test them like the past paper? Then?
Why what?
Why none of our exams like the past papers?
Well, some did.
Kim was.
Why
Which time was alright? But maths was crazy.
Mine was so easy. It was hard.
Alright, we don't have time to waste. Next topic.
Is there any experiment about ways? Yeah, so like, is there any experiments commonly tested?
Experiments.
Yeah.
Is it young?
What? Yeah, so what does that have to do?
It's all waves.
So the Young's double slit is with interference. That's like the first few things in physics. And that's simple. You can revise that by yourself.
Is it when like, is it the short one they interfere with it?
So series of dark and white fringes. So it's like, so you start off with one wave, it creates 2 waves, and the waves interact with each other, and when waves interact like this, there's constructive and destructive interference, in phase, out of phase. So at the wall, you all can revise this by yourself. This one is nothing really. You see a series of light and dark fringes. All right, talk to me. We're getting ready to close up here. So what y'all could do is like walk with questions for tomorrow. So try to 5 to, you see. What's the time now? Going to 9? Maybe like 5 to 9 I'll have it, right? So we'll be back live tomorrow. Somebody said do transformers next. So transformers is as simple as it gets, because transformers is just VP over VS is equal to N. We did this earlier, so if you watch it live, NP over NS, IS over IP. And then they'll probably use these equations or efficiency, which is just a percentage stuff. So we did some examples on this earlier. That person probably just come on who asked about transformers. You can pull back and watch it. Any other pattern topics, people? So you could revise as much as you can between tomorrow and 5.
Okay, what's the method if I genuinely?
Why not like you're in this situation? That's not your situation.
What part? I'm not gonna try with the concepts. I've tried before. You had a lot of information. It's helpful, but the time I have is not working. Like I don't have the time.
That's one wait. Say the question again.
Like I'm not gonna read the concepts anymore.
Mm-hmm.
It's helpful, but there's no time to absorb it. Like I need like rapid topic covers that get like.
Well, one of the things with physics, why I love physics so much is it's very important with how you learn, there's an efficient way to learn physics and there's an inefficient way. Like, so you see, for everything, I was able to like quickly print out a mind map of what you need to know and then how the question is structured. That's what you're trying to do for yourself as well. So physics, you should understand that the topics, there's three things. There's like the theory, just the raw theory, understanding raw theory. There's like definitions. Theory include like diagrams. There's like just straight up definitions. And then there's the maths. So all of the questions, every single question in physics follows the same format. What is Newton's second law? Define Newton's second law or something they give you with it, and then they give you some question to do along Newton's second law. So this part, I told myself when I was your age, anytime I have an exam to memorize anything, I am going to easily get 100%. Because if it's just, you mean to say I just need to learn everything, all these definitions, and just go back and do it in the exam? Oh, why not get 100%? I just need to memorize it. so just memorize and get it.
Alright.
It's not do the calculation for person like.
I can make. I understand that I can make a mistake in the maths, but what do you mean? I just need to learn exactly this and put it back in the exam. So that means I was very confident in my ability to memorize things very quickly. So for example, what subjects you guys do? History. Who is doing history here? You? Give me something. Give me something in history that you have memorized.
I memorized?
Yes.
Hopefully.
That's like for 3 months.
There's nothing for 3 months.
Like 6 months.
What subjects are you guys doing? You all did biochem? What was something that you memorized in chem that came? Isotopes. So which also overlaps.
No, the isotopes.
So what is an isotope?
Things that have the same number of protons.
So let's say I didn't know what an isotope is. So we'll say atoms of the same element with different mass numbers, but same proton number. So Kirsten is from my class, and some of the people here from my class, that's what I taught them for memorizing physics, that active recall method. Active recall and space repetition. So what they would do is, you were saying something over and over that was worrying me. You say, I fed up reading concise, I can't read the concise, read. There's no reading. So most people, when they're studying, spend a lot of time studying and very little time recalling. So let's say I never knew this formula, definition, but same proton number. The average person would just spend like most of the time trying to memorize it instead of trying to recall it. I would read this once, try to think about it. That's the only time I spend studying. I do actually the opposite. I spend like this amount of time studying and all the rest of the time trying to active recall, trying to recall it back. So which means when I check students and I ask them if they study for themselves, how much physics you study, the student who can show me the most amount of work that they do for themselves and past papers and their own notes and their own scribbles and not just reading over the same thing over and over, that is the student who will do best or who spend the time the most efficiently. So between now and tomorrow, you can't tell me you will study between now and tomorrow and you just probably write 2 or 3 pages worth of stuff. You're supposed to be writing dozens of pages by tomorrow. You're supposed to just be ripping through everything and just turning. Ask Kirsten and all of them. It's the same. She's saying it. You have to believe her. It's active recall. Active recall. So within now and tomorrow, you all have more than enough time to learn up the entire syllabus if you're writing. You're supposed to be coming in 5 p.m. to that session anyway with your hands feeling Like you can't write anything because like let's say you want to learn this isotopic. Now listen to me. It's not penmanship. I'm not telling you to go and write over the notes. That's not helping. You have to actually try to remember it. So like let's say you're trying to learn isotopes. You go to the new page. I understand what I mean. Okay, so apparently an atom could have the same number of protons, different number of neutrons. And I go to the new page and I just try to write it one time. That's as much time as I spend studying it. And I can't remember how to start. That's what's happening most definitions. You can't remember, like the connectors and understanding something about what same protons, different neutrons. And something I can't remember how to start. Then I go back and check my mistake. Atoms of the same element. Atoms. So it's two ways of saying the same thing. Atoms of the same and same in the middle. And every time I recall something, I use the error to kind of like help me. And do you think I'll fall in the trap of trying to memorize it off now? No. I immediately go back to a new page and try again. Atoms of the same element that have same proton number, different mass number or neutron number. Was it mass or neutron? I had neutron just now. It's not neutron. It should be mass. And I just write it again. And that's it. And by doing that, you do a couple things one time. You know how much you know for sure. Because in the exam, you don't psychically tell the examiner the answer. You have to write the answer. So you get to know immediately how much you know, because this is going to stay with me for sure for like 2 hours. And that's where the space repetition comes in. I go back and write it again. And if I forget, oh shucks, I forget how to start again. Don't panic. That's happened. Just go back and watch it. Oh yeah, atoms of the same element, and it reinforced now. That is what you need to do. So you're going to be doing a lot of active recall. That's how you learn things fast, yeah, efficiently. Most of the time when this happens, students will be like, this is the longer method. No, it's the shorter method by far. By far, it's the shorter method. It just is because it's not the lazy method. You actually have to do the work. All right, people. Later, YouTube. We can see you later tomorrow.